In order for polygons to be similar, their corresponding angles are going to be congruent to each other. However, their corresponding sides are going to be proportional. This is an example of a similarity statement where the order matters. The angles match up and are congruent, but the sides are only proportional. Take a look at this example and write it down in your notes. Pause the video as you need it. As we look at the two triangles, we need to look at the similarity statement and come up with a proportion. The key here is to be consistent. If I choose x first, I need to see what x is similar to. So I look at the similarity statement and look at AC. AC corresponds with ST, so I can match up that side. And then I need to pick a number that corresponds with 5. Well, that goes with LS, and LS corresponds with BA. So I can set up a proportion. Now I can cross multiply and solve. I would do the same thing for the other variable, for the y value. I need to see what LT corresponds with and then be consistent. If I choose that number on top, I've got to go and get something from that same triangle to match up with it. The key to setting up your proportions is to keep them consistent, grabbing numbers from the same triangles in that same order. Cross multiply and solve. Copy this example down. This time it is a rectangle, or so it appears to be a rectangle. We've got a similarity statement up at the top, and they want us to solve for x. So we're going to match up. The key to writing your proportion is being consistent. There is more than one way to write this. If I choose x, I could match it up with 27, then I have to go back and get 6 and match it up with 18. Or you could stay within the same shape and go x over 6 is equal to 27 over 18. If you are consistent with the way that you set it up, you'll still get the same answer. Copy this word problem down. For some of you, you might want to even sketch a picture. The key to this one is to be consistent. We're talking about a tree and a person. You can work with the tree's height and the tree's shadow and the person's height and the person's shadow. Or you can talk about tree height, tree shadow, person shadow. The key is to pick one and be consistent on both sides of your equal sign. So on this one, I'm going to go in this direction. Here's my equation, and now I can cross multiply and solve. When we're looking at the ratio of similar polygons, we are matching up their corresponding sides. You can also match up their corresponding perimeters, which is just the ratio of A to B. If I were to match up their areas, it would be their ratio of their corresponding sides squared, or their scale factors squared. If you were to write a ratio for their volumes, it ends up being cubed. So take a look at this example. We've got information about sides, but yet it gives me the ratio of the perimeters from cat to dog is 3 to 2. It is perfectly fine for you to work with perimeters and corresponding sides all in the same problem. Again, the key is going to be consistency. They list cat first and dog second, so that 3 in the ratio of 3 to 2 goes with cat, and the 2 goes with dog. So we're going to have to be consistent and go cat, dog, cat, dog. So 3 over 2 needs to match up with 6 over y. 6 and y correspond, but they had to come from the same triangles. Now cross multiply and solve. So on this problem, I've got information about sides and information about perimeters. It's completely fine for you to use all of that within the same problem. Some of you on this problem might actually pick up on scale factor and see what's going on between the 12 and the 4. So you know mathematically what's going to happen from the 60 to the question mark, the one that we're looking for, that x. I recommend writing an equation and cross multiply and solve. So I mentioned scale factor earlier. It's the ratio of the new image to the original image. You're matching up their corresponding sides, or you're matching up the corresponding perimeters. If your scale factor is a number greater than 1, the shape is getting bigger. If it's a number less than 1, it's getting smaller. So on this first purple example, if I'm going to go new to original, this shape has gotten bigger. So new is on top, original is on the bottom, which reduces down to a scale factor of 3 to 1. On this next one, I've got triangles, and I've got more than one side to look at, but it's still new to original. I can pick any of these sides, small, medium, or large, and match it up with any of the other ones from the other triangle, small, medium, large. They would all reduce down to the same scale factor of 1/2. This shape has gotten smaller. When given coordinates and you're going to apply a dilation, an enlargement, or a reduction, all you have to do is multiply the value, the scale factor, to the x and the y values. Remember from last year in coordinate algebra, once we move these shapes, we use the prime on those letters. So just multiply times 2. Pause the video and see if you can figure out the answers on your own first. What's expected to happen on this scale factor of 1/4? Well, it should get smaller. It's a reduction. All you're going to do is multiply times 1/4 to your x and your y value. And it's not that bad with the calculators that we're working with. So pause the video and see if you can get your answers on your own before you see them on the screen. Take a look at this one. What would the triangle do with a scale factor of 1/2? That's right, get smaller. So you would need to identify the 3 vertices of the triangle and then multiply times 1/2 to each of those values. K equals 2 on this one, so this is an enlargement. So we're going to look at the endpoints, take the x and y value, and multiply them by 2.